What if the actual size of the universe is completely different from what scientists imagined? In the deepest stretches of cosmic darkness, far beyond the farthest galaxies mapped by even our most advanced observatories, a question lingers like a silent electrical charge. What if the universe is nothing like the one scientists think they understand? Imagine waking up tomorrow to headlines announcing that the true size of the cosmos differs not by millions or billions of light years, but by orders of magnitude that dwarf every measurement ever taken. Imagine the entire cosmic model, carefully built over centuries, suddenly trembling under the weight of a discovery so disorienting, so colossal, that it threatens to rewrite reality itself. This is not a hypothetical thrown casually into conversation. It is a frontier question emerging from the cutting edge of cosmology, where the measurable ends and the unimaginable begins. For centuries, humans have tried to quantify the universe with tools that evolved from rudimentary telescopes to spaceborne observatories perched 1,000,000 miles beyond Earth. Each generation confidently believed it understood the cosmic scale, until the next discovery made their certainty look quaint. Ancient astronomers once pictured the heavens as a fixed sphere of shimmering points just beyond the atmosphere. Later, scholars imagined a cosmos only slightly larger, a decorative dome encasing a handful of celestial lights. Even as telescopic power increased, scientists still thought all of existence was contained in a single galaxy. That belief shattered in the early 20th century when astronomical pioneers realized those faint smudges in the night sky were not nebulous clouds, but entire galaxies, millions of light years away. The universe expanded, not physically, but in human understanding, by factors so large they nearly crushed the imagination. But here lies the deeper question. If our models have been repeatedly humbled by new discoveries, why should we assume that now, suddenly, humans have grasped the true size of the universe? What if the cosmos is preparing to reveal yet another twist? The possibility is unsettling and intoxicating. Scientific progress is littered with moments where once solid truths crumbled under the force of new data. And nowhere is that more evident than in attempts to measure the universe's boundaries. Every measurement of cosmic size is built on a fragile foundation, the assumption that light behaves predictably across vast distances, that space expands according to models we can compute, and that the observable universe provides meaningful clues about the whole. But what if these assumptions contain hidden errors? What if space stretches differently in remote regions? What if the universe bends, wraps, folds, or behaves in ways too subtle or too grand to detect with existing instruments? The familiar diameter of the observable universe, about 93 billion light-years, might represent nothing more than a tiny bubble inside an ocean so limitless that numbers lose all meaning. To understand how uncertain our measurements truly are, consider the way scientists estimate cosmic distances. They begin with parallax, measuring the apparent shift of stars as Earth orbits the Sun. But that method collapses at larger distances, where the shift becomes too small to detect. Astronomers then rely on standard candles, objects like Cepheid variable stars, whose intrinsic brightness can be calculated. But even that method depends on assumptions about stellar behavior, chemical composition, and environmental influences. Beyond that, scientists use type Ia supernovae, explosions so bright they briefly rival galaxies. These supernovae act as cosmic yardsticks stretching into the deepest observable regions. But what if these candles flicker? What if their brightness varies subtly across cosmic epochs, influenced by unknown physics? A slight miscalibration in brightness can lead to monumental miscalculations in distance. A 1% error in luminosity becomes a 10% or 20% discrepancy when scaled across billions of light years. Now imagine errors not of 1%, but of 5% or 10% or more. The universe's size could be drastically different, smaller, larger, or so structurally complex that our human-made measurement ladder simply collapses under its own assumptions. Even more unsettling is the fact that each rung of the cosmic distance ladder depends on the one below it. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae calibrate redshift distance relationships used to measure expansion. A flaw in any foundational rung propagates upward like a crack through glass, distorting every subsequent measurement. If even a single element is wrong, if Cepheids behave differently in metal-poor galaxies, if early supernovae evolved differently than modern ones, if redshift is influenced by some unknown cosmic medium, then the entire cosmic framework may be wildly off. Then there is the problem of cosmic expansion. The universe is not a static backdrop, but a restless, dynamic, inflating fabric. Space stretches, galaxies drift apart, and the very structure of reality bends away from our attempts to quantify it. When we observe distant galaxies, we see them not as they are, but as they were billions of years ago. The light reaching us traveled through a universe that changed dramatically during its journey. This distorts distance in ways that are nearly impossible to perfectly account for. A galaxy whose light took 13 billion years to reach Earth may now sit 30, 40, or 50 billion light-years away due to expansion. Every cosmic measurement is a moving target. If that were not complex enough, recent discoveries have further destabilized scientific confidence. High redshift galaxies captured by the James Webb Space Telescope appear too massive, too developed, too bright for the early universe. These anomalies challenge models of star formation, matter distribution, and cosmic timelines. Some researchers propose revisions to inflation theory, claiming the early universe may have expanded unevenly or asymmetrically. Others suggest modifications to general relativity. A few argue that dark matter or dark energy could behave differently across regions of space, warping structure formation and expansion measurements. If the underlying physics shifts over cosmic distance, then any assumption that the universe behaves everywhere the same may be deeply flawed. And if that assumption falls, the very concept of measuring the universe's true size becomes nearly impossible. We would be trying to measure a world whose rules change depending on where and when you look. There is also the possibility of cosmic topology, the overall shape of the universe, being something far stranger than the simple models taught in schools. Space might be finite but unbounded, like the surface of a sphere, looping back on itself in higher dimensions. Travel far enough in one direction, and you might eventually return to where you started without ever encountering an edge. In such a universe, determining size becomes meaningless, because boundaries do not exist in the conventional sense. Alternatively, space could be shaped like a torus, a multidimensional donut, or a more exotic manifold that defies geometric intuition. In such scenarios, light could circle the universe multiple times, creating repeated patterns in cosmic background radiation. Detecting such patterns would provide clues about size, but only if they are large enough or our instruments sensitive enough. If the universe is vastly larger than the observable bubble, those patterns may be so spread out that they vanish into noise. Even the idea of observable universe may mislead us. It implies a distinction between what we can see and what exists beyond our cosmic horizon. But the horizon itself is not a boundary of existence, only a limitation imposed by the finite speed of light. Beyond that limit, the universe may extend for trillions, quadrillions, or googolplexes of light years. It could stretch infinitely, with no physical boundaries. Or it could be part of a multiverse, where our cosmic bubble is one node in an endless foam of universes spawning and expanding independently. If we live in an infinite cosmos, then no measurement, no matter how advanced, could ever reveal its true size. Our observable region would remain a microscopic fraction, a cosmic grain of sand in a desert without end. Every galaxy we see, every cluster we map, every filament we trace would represent only the shallowest surface of a structure, so enormous that human numbers crumble under its scale. But what if the opposite is true? What if the universe is smaller than we think? What if its actual boundaries lie closer than the cosmic horizon suggests, hidden behind curvature or topology? A closed universe could create illusions of distant galaxies that are actually much nearer, but visible from different angles due to space curving around itself. Light could wrap, reflect, or refract across cosmic geometry in ways we do not yet understand. Under such a model, the universe might be a compact cosmic sphere whose size has been misinterpreted due to the non-linear effects of expansion and curvature. Over the last decade, several anomalies in cosmic microwave background data have hinted at unexpected alignments, patterns inconsistent with an infinite isotropic universe. These anomalies could point to a universe smaller, more structured, or more geometrically complex than believed. If these hints prove meaningful, they would fundamentally alter the concept of cosmic size. And then there is dark energy, the mysterious force accelerating cosmic expansion. If its influence evolves over time, the universe's past expansion rate may differ dramatically from its current rate, leading to major misinterpretations of distance, age, and size. A universe with variable dark energy could expand in irregular bursts, creating pockets of rapid inflation and slower growth. In such a case, extrapolations we make based on current expansion could be wildly inaccurate. All of these possibilities lead to one profound truth. The universe's true size may be completely different from anything scientists have imagined, not because they lack intelligence, but because the cosmos is larger, stranger, more dynamic, and more deceptive than human intuition can grasp. Imagine standing on a quiet hillside at night, watching the sky stretch into a shimmering tapestry of stars. The air is still, the horizon wide, and everything feels enormous. Yet even that sense of immensity barely scratches the surface of reality. Overhead lies a universe so vast that our entire Milky Way, home to hundreds of billions of stars, shrinks to a tiny glimmering fleck in cosmic darkness. And still, this incomprehensible immensity might represent nothing more than the tiniest scrap of a much larger whole. What if everything we think we know about the size of the universe, every measurement, every assumption, every carefully calculated parameter, is not merely incomplete, but fundamentally misguided? To even ask this question is to challenge centuries of scientific confidence. Humans have always been obsessed with boundaries, where the ocean ends, where the atmosphere thins, where the continents lie. We map, measure, quantify, and categorize, because doing so gives us the illusion of mastery over the world. But space is not like Earth. The cosmos does not yield easily to human attempts to determine its size. In fact, every time astronomers think they have caught a glimpse of its true scale, the universe pulls a familiar trick. It grows, expands, shifts, revealing new layers that dwarf previous estimates. It has been a constant cycle of humility, a repeated reminder that human perception is limited and cosmic reality is not obligated to fit within our understanding. Consider the history of cosmic measurement. Ancient civilizations believed the sky was a dome just a few miles high. Later, medieval scholars imagined crystalline spheres encasing the stars. Renaissance astronomers believed the cosmos ended just beyond Saturn. Even after the telescope transformed science, humanity still thought the Milky Way was the entire universe. This was an assumption that endured well into the 20th century, until Edwin Hubble revealed that those faint smudges in the night sky were actually galaxies far beyond our own. Overnight, the universe grew from 100,000 light-years across to millions. Later discoveries expanded it to billions. Modern estimates place the observable universe at 93 billion light-years in diameter, and yet, every one of those numbers has already been proven incomplete in its time. Why assume the most recent one is any different? The deeper we peer into space, the more the universe behaves like a magician skilled in misdirection. Its secrets hide behind illusions of distance, distortions of space-time, and tricks of cosmic perspective. Light from distant galaxies arrives warped, stretched, shifted, or delayed by gravitational forces. Expansion drags galaxies farther apart during the very process of observing them. The cosmic microwave background, the oldest light we can detect, forms a glowing wall that blocks any electromagnetic information from earlier than 380,000 years after the Big Bang. And even beyond that, theoretical boundaries blur, hinting at regions we cannot see, measure, or ever reach. What if our universe is shaped in a way that prevents us from perceiving its true size? Imagine space not as an infinite flat expanse, but as a curved or folded structure. In a curved universe, light travels along arcs, sometimes looping back on itself. In a folded universe, distant regions might be physically much closer than they appear, hidden behind the geometry of dimensions we cannot visualize. Picture walking across a sheet of paper that has been folded into a loop. You could reach the opposite edge far faster by cutting across the fold than by following the surface. Space might behave in ways even more intricate, wrapping, twisting, or extending into higher dimensions. These shapes could make the universe appear either larger or smaller than it truly is, depending on direction, curvature, and topology. Human intuition collapses under such possibilities. We evolved to understand distances measured in footsteps, not light years. Our brains recoil at numbers like 1024 kilometers or 1080 particles. But the universe is not obligated to obey the limits of human comprehension. It may be constructed on scales that exceed any number humans are capable of writing, imagining, or conceptualizing. The real measurement might be so large, it can only be expressed in theoretical infinities. Here lies the unsettling idea. The universe may not merely be larger than we think, it may be categorically larger, existing in a realm of scale where human concepts like size and distance lose all relevance. If the cosmos is infinite, size becomes meaningless. Infinity is not a number that can be compared with billions or trillions. Infinity has no magnitude, no boundary, no upper limit. In such a universe, even the largest structures we observe become statistically insignificant. But what if the opposite is true? What if the universe is smaller, much smaller than our models predict? This is not as absurd as it sounds. A finite universe could masquerade as a much larger one if space wraps around itself. Light could travel in loops, making distant galaxies appear unique, when in fact, they are repeated images of the same object seen from different directions across cosmic curvature. Scientists have searched for repeating patterns in the cosmic microwave background that might indicate a finite closed universe, but so far, the evidence has been inconclusive. Yet even inconclusive results leave the door open to possibility. Measurement becomes even more complex when we consider cosmic inflation, the rapid expansion period that occurred fractions of a second after the Big Bang. Some models predict that inflation expanded the universe far beyond the observable region, to sizes so enormous they defy computation. Others suggest inflation never ended, producing an infinite multiverse with endless bubbles of space-time. Our universe, in this scenario, is just one of countless others floating in a sea of cosmic expansion. Each bubble may have its own laws of physics, its own form of matter, its own dimensions, and its own definable size. But if space extends infinitely through the multiverse, any attempt to measure a single bubble, ours, becomes like trying to calculate the size of one droplet in an endless ocean. And then there is the possibility that the universe's size shifts over time. Not merely its expansion, which scientists accept as fact, but its fundamental spatial boundaries. Some theories propose that dimensions can stretch, shrink, fluctuate, or even disappear across cosmic epochs. Early universe conditions might have supported different geometric configurations. Smaller, denser, more compact dimensions that expanded or transformed as matter cooled. If the universe changed shape in the past, its current shape, and therefore size, may be a temporary phase, a cosmic season, a brief geometry in a much larger story. Dark energy complicates everything. This mysterious force accelerates expansion, but its nature remains unknown. Some theories suggest dark energy may vary across time or space. If true, regions of the universe could expand at different rates, creating pockets of space vastly larger or smaller than others. Our observable bubble may be expanding slowly compared to more distant realms, creating an illusion of uniform size. Or the opposite could be true. We might live in an unusually fast expanding region, isolated by cosmic acceleration from more stable areas that behave differently. Compounding this uncertainty is the Hubble tension, the disagreement between expansion rate measurements made from nearby galaxies and those derived from early universe observations, like the cosmic microwave background. The mismatch suggests either that the local universe behaves differently than the average universe, or that our models miss something fundamental. Either interpretation implies that our understanding of size may be radically flawed. Even gravity complicates the question of size. Dark matter, which shapes galaxies and cosmic structure, interacts only through gravity and might behave differently across vast distances. Some alternative gravity theories propose modifications to general relativity that become significant only at the largest scales. If gravity weakens, strengthens, or warps differently across regions, the shape and expansion of the universe could vary dramatically. In such a world, Trying to measure size becomes like trying to measure the volume of smoke, constantly shifting, amorphous, impossible to define. All these uncertainties leave us with a profound realization. Our understanding of the universe rests on a fragile web of assumptions, approximations, and limited observations. Every measurement we make depends on light behaving consistently, physics remaining uniform, and space maintaining predictable geometry. But if any of these break down across cosmic distances, then our entire understanding of size may be nothing more than a comforting illusion. The universe might be smaller, it might be larger, it might be infinite, it might be a multiverse, it might be folded, curved, or shaped in dimensions we cannot visualize. It might even be dynamic, changing shape over time. The truth is that the cosmos does not reveal itself easily. It leaves clues in starlight, whispers in background radiation, and hints in the distribution of galaxies. But it also hides its secrets behind horizons, distances, distortions, and physical limits that prevent full comprehension. And yet, this is what makes the question so electrifying. To contemplate the true size of the universe is to confront the limits of human knowledge and simultaneously expand them. It is to face the daunting possibility that the cosmos is not merely bigger than we imagined, but stranger, richer, deeper, and more complex than our species has ever dared to dream. What if everything humans believe about the cosmic scale, every diagram, every textbook, every lecture, every simulation, rests upon a foundation so fragile that a single discovery could shatter it like glass? What if the universe is not merely misunderstood in its details, but misinterpreted in its entirety? To grapple with this question is to confront a possibility, both exhilarating and terrifying. The possibility that the cosmos may be structured in a way that fundamentally deceives our senses and instruments, creating illusions of distance and scale that mislead even the sharpest scientific minds. Start with a simple idea. The universe is expanding, not slowly drifting apart as grains of sand scattered by a breeze, but rushing outward in a vast cosmic surge. Galaxies recede from one another in every direction, and the farther away a galaxy is, the faster it appears to be moving. This observation, first made in the early 20th century, introduced a radical new concept. The universe has no fixed size. Its boundaries stretch, its fabric inflates, its scale evolves. Yet even this understanding might be incomplete. What if expansion itself behaves in ways we cannot imagine? Could the universe expand faster in some regions, slower in others, leaving us with a distorted sense of cosmic geography? Imagine standing on a boat in the middle of the ocean. If the water around your boat drifts at one speed, while the water farther out moves faster or slower, the surface would stretch unevenly. Any map you drew of the sea would be skewed by those shifting currents. Now replace the ocean with space-time and the gentle drift of water with the violent expansion of the cosmos. Measuring the size of the universe becomes an act not of simple mapping, but of trying to chart a constantly shifting current that changes differently in every direction. But the complexity doesn't stop there. The universe is filled with matter and energy that astronomers cannot see. Dark matter and dark energy, components of reality that shape cosmic behavior more than anything else. Dark matter forms the skeleton upon which galaxies assemble. Dark energy drives the acceleration of expansion, yet both remain invisible, undetectable except through gravitational influence. What if these hidden forces behave differently across immense distances? What if dark energy intensifies in certain regions or weakens in others? What if dark matter forms structures far beyond the visible horizon, warping geometry in ways we cannot detect? This uncertainty creates a cascade of possibilities. The universe might be far larger than we believe, because expansion is far more aggressive in distant regions than in our local area. Light from remote stars could stretch beyond recognition, becoming so diluted and redshifted that our instruments can no longer detect it. These distant structures might be receding faster than the speed of light, not because they violate physics, but because space itself expands between us and them. In such a world, the observable universe becomes a tiny bubble isolated by cosmic motion, surrounded by regions forever inaccessible. On the other hand, the universe could be far smaller than we think. If the cosmos curves back on itself, light might loop around multiple times, giving us repeated images of the same galaxies. A galaxy we believe to be 10 billion light-years away could be a mirror image of a galaxy only a fraction of that distance, its light stretched and bent by cosmic curvature. Scientists have searched for such repeating patterns in the cosmic microwave background, the afterglow of the Big Bang, but have found none definitive. Yet, the absence of evidence is not evidence of absence. If the universe is curved at scales beyond the observable horizon, no detectable pattern would appear. Another possibility arises from inflation, the rapid expansion that occurred microseconds after the Big Bang. Some theories propose that inflation did not stop everywhere at once. Instead, it may have ended in patches, creating a universe composed of bubble-like regions expanding at different rates. In this model, known as eternal inflation, our observable universe is merely a bubble inside a greater cosmic foam. Our bubble might be enormous, or it might be tiny. Without access to space beyond the boundary, scientists simply cannot know. The true size of the larger multiverse might be infinite, with new bubbles forming constantly in a never-ending cosmic bloom. Even if the universe is finite, its shape may be so complex that conventional measurements break down. The cosmos could be shaped like a multi-dimensional donut, a Mobius-like surface, or a twisted manifold where traveling in one direction eventually brings you back to your starting point. In such cases, size becomes a misleading concept. What is the size of a shape that loops back on itself? What is the distance between 2 points if space folds? Humans are accustomed to linear measurements, but the universe may obey geometric rules far more exotic and unintuitive than the straight-line distances measured on Earth. Cosmic voids, vast regions with little matter, add further uncertainty. These enormous empty spaces, some hundreds of millions of light-years across, create gravitational imbalances that distort the motion of galaxies. Light passing through voids travels differently than light passing through dense clusters, complicating distance calculations. If voids are larger or more numerous than currently believed, or if they extend beyond the observable boundary, they could create illusions of scale that mislead astronomers. What if our cosmic neighborhood happens to lie near an unusually large void, skewing local measurements of expansion and mass distribution? Our position in the universe may distort our perception of its size, just as a person standing in a canyon might mistakenly believe the entire world is carved into deep valleys. A further complication arises from gravitational lensing, the bending of light by massive objects. Lensing can magnify, distort, or create multiple images of distant galaxies. It can also hide objects entirely behind massive clusters or warp them into arcs and streaks. If massive structures lie beyond the observable horizon, their gravitational influence could subtly distort the light we see, creating errors in distance estimation. These distortions, when scaled across billions of light-years, could lead to colossal misinterpretations of cosmic size. Even the cosmic microwave background, the oldest observable light, may deceive us. It appears uniform, with tiny temperature fluctuations that reflect early density variations, but its smoothness may mislead scientists into believing the universe is flat and infinitely large. A curved or closed universe could still produce a microwave background that appears flat within our limited observational region. And if there exist regions beyond the cosmic horizon where conditions differ, different densities, different temperatures, or different inflation dynamics, those regions could exist in a universe far more complex than the neat models drawn by cosmologists. The Hubble tension adds yet another layer of mystery. Local measurements of expansion conflict with measurements made from the early universe, implying either that something is wrong with our models or that the universe behaves differently in different eras or regions. If the expansion rate has changed over time, the universe's size may have changed more dramatically than models predict. Alternatively, if different regions expand at different rates, size becomes a relative concept dependent on where one stands. Even more unsettling are suggestions from quantum physics. Some theories propose that space itself is quantized, that it consists of tiny, discrete units like pixels on a screen. If so, the universe might not be a smooth continuum, but a mosaic of quantum cells. The number of these cells, and the way they interact, could determine the universe's effective size. Quantum fluctuations in early cosmic history could have created variations in spatial geometry that stretch or compress regions of the universe unpredictably. All these possibilities share a common theme: uncertainty. This uncertainty is not due to lack of intelligence or effort, but because the cosmos refuses to reveal its true form easily. Humans measure the universe using light, gravity, radiation, and mathematical models. But if the universe shapes, bends, or distorts these signals, then our tools, no matter how advanced, may always tell an incomplete story. To contemplate that the universe's size might be fundamentally different from what scientists believe is to acknowledge the limits of human perspective. It is to stand at the edge of understanding, peering into a darkness that stretches far beyond imagination. And it is to realize that the true cosmic scale may forever lie just out of reach, hidden behind horizons we cannot cross, and wrapped in mysteries we cannot untangle. Yet despite these uncertainties, the pursuit continues. Humans measure, question, refine, and explore, not because the universe is easy to understand, but because its mysteries ignite a spark of curiosity that defines our species. The true size of the universe may be unknowable, but the journey toward discovery is what makes the question worth asking. There is a strange moment in astronomy, one that every scientist encounters sooner or later, when the universe refuses to behave as expected. Telescopes reveal objects that seem too bright, too distant, too old, or too massive. Equations collapse under anomalies, and constants wobble where constancy is assumed. It is in these cracks, these subtle betrayals of predictability, that the most profound questions arise. Among them is one that whispers with relentless persistence. What if the universe is far larger, far smaller, or far stranger than humans have ever imagined? What if each measurement we confidently accept is merely a faint echo of a reality far beyond comprehension? To explore such a possibility, imagine stepping back from human knowledge, past the equations, past the telescopes, past the assumptions, and looking at the cosmos as if for the first time. What would you see? Perhaps not a neat, symmetrical sphere 93 billion light-years across, but something far more unpredictable. The universe may not resemble the orderly maps drawn in textbooks. Instead, it might be asymmetrical, textured, fractured by gravitational forces, or shaped by physics that operate differently across its expanse. Humans like to imagine the universe as uniform, but nature rarely respects uniformity. Start with the idea of cosmic homogeneity, the widely accepted assumption that, on sufficiently large scales, matter is distributed evenly throughout the universe. This principle underpins every major cosmological model, from the Big Bang theory to modern simulations of galaxy formation. Without homogeneity, the equations break. Without homogeneity, the entire framework collapses. And yet, when astronomers map the large-scale structure of the universe, they find vast filaments of galaxies stretching hundreds of millions of light-years, separated by enormous voids. They find clusters so massive they defy current models, and structures so large, like the Hercules Corona Borealis Great Wall, that they push the limits of what homogeneity should allow. If these structures are not mere exceptions, but hints of larger unseen patterns, the universe may be orders of magnitude larger than we think. The observable universe may be a tiny window into a far grander cosmic architecture, an architecture defined not by neat uniformity, but by chaotic variation. Now consider the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. This horizon is not the edge of the universe. It is the limit of what is observable. The actual universe extends beyond it, but by how much? 10 times farther? 1,000? 1,000,000,000,000? Human intuition breaks down at such scales, and current technology cannot reveal what lies beyond. If the universe continues indefinitely, its true size may be infinite. But even infinity comes in varieties. Mathematicians describe different sizes of infinity, some greater than others. The universe could be an infinite fractal, repeating patterns across scales so vast they defy conceptualization. Or it could be a finite but unbounded shape, a cosmic loop, a higher dimensional sphere, a hyperbolic manifold whose size cannot be expressed in conventional measurements. One theory suggests that the universe could be shaped like a multidimensional torus. In this scenario, traveling far enough in one direction would bring you back to your starting point, but only after traversing unimaginable distances. Another theory proposes that the universe may have a saddle-like curvature, allowing it to expand infinitely in some directions, while curving subtly in others. These shapes distort light in ways that create illusions of size, making distant galaxies appear farther or closer than they truly are. If cosmic topology bends light around the universe like a lens, then our entire cosmic map may be a distortion, a projection of a geometry we cannot directly observe. Another complication arises from the nature of time. Humans assume time flows steadily, but cosmic time is warped by gravity, velocity, and energy density. In regions of intense gravitational pull, time slows. In vast voids with low density, time may flow faster. If regions of the universe experience time differently, then measurements of distance and size become even more difficult. A galaxy in a region where time flows faster may appear older than it is, affecting assumptions about distance, redshift, and expansion. A galaxy in a region where time flows slower may appear younger or closer. These distortions accumulate over billions of years, potentially creating enormous perceptual errors. Now imagine that the expansion of the universe is not uniform. What if cosmic inflation, the rapid expansion after the Big Bang, did not occur evenly? Some regions may have stretched more than others, creating pockets of space vastly larger or smaller than expected. These pockets may be separated by cosmic walls or inflationary boundaries, forming distinct zones with different expansion histories. If the observable universe lies within such a pocket, our measurements reflect only local conditions, not the true cosmic scale. Beyond our pocket, space may be expanding faster or slower, or not at all. There may be regions where galaxies are densely packed, and others where they are so widely spaced that detecting them becomes impossible. Dark energy complicates matters even further. It is the force driving cosmic acceleration, but its nature remains unknown. It could be constant, or it could vary with time and space. If dark energy increases in strength as the universe expands, the expansion rate could accelerate faster than predicted, pushing distant regions beyond observational reach more quickly than expected. Entire galaxies could slip over the cosmic horizon, disappearing from view as space stretches faster than light can travel. If dark energy changes over time, its fluctuations could cause the universe to expand unevenly, making some regions appear larger and more distant than they actually are. Dark matter also plays a role in determining the universe's structure. If dark matter interacts differently in different regions, if it clumps more readily in some areas, or behaves differently under extreme conditions, it could distort the cosmic web on large scales. These distortions influence the motion of galaxies, the curvature of space, and the propagation of light. A galaxy cluster surrounded by dense dark matter may appear farther away due to gravitational lensing. A void devoid of dark matter may alter the path of light, causing distant galaxies to appear closer. Over billions of light years, these effects compound, creating errors that ripple through every measurement of size. Even the cosmic microwave background, the oldest light in the universe, offers hints that the universe may not be as uniform as once thought. Subtle anisotropies, or temperature variations, appear across the sky. Some alignments, like the axis of evil, a mysterious correlation in temperature patterns, challenge the assumption of isotropy. If these patterns reflect underlying structures beyond the observable universe, they could indicate a cosmos far more complex and structured than expected. Then there is the possibility that the universe contains hidden dimensions. String theory and other advanced models propose as many as 10 or 11 dimensions, most of them curled up at scales too small to detect. But what if some dimensions are not small? What if they are large, extended, and influential? A universe with large-scale extra dimensions would behave in ways radically different from a three-dimensional cosmos. Light could curve into these dimensions, disappearing from 3D space. Gravity could leak into higher dimensions, weakening over distance. The true size of the universe could exist partly in dimensions humans cannot perceive, making any measurement incomplete by definition. Quantum mechanics introduces yet another layer of uncertainty. At the smallest scales, particles behave unpredictably, popping in and out of existence, fluctuating in energy, and defying classical intuition. Some theories propose that space-time itself has quantum fluctuations, tiny ripples that accumulate over cosmic distances. If space-time fluctuates on the smaller scales, these fluctuations could distort distance measurements across billions of light years. The universe might appear larger or smaller, depending on the cumulative effects of these fluctuations. And then there is the multiverse hypothesis, the idea that our universe is just one of many. In this scenario, the question of size becomes even more complex. How do you measure the size of a universe that might be one bubble in an endless sea of cosmic variation? How do you quantify a reality where new universes may form constantly, each with different laws of physics and different spatial dimensions? In such a multiverse, our universe's size could be trivial compared to the whole, or it could be one of the larger bubbles. Humans have no way to know. The horizon prevents any exchange of information between bubbles. The true cosmic landscape remains hidden. At the heart of all this uncertainty lies a profound truth. Humans may never know the true size of the universe, not because scientists lack intelligence or technology, but because the cosmos may be structured in ways fundamentally inaccessible to human perception. The observable universe is not the universe. It is only the part we can see. Beyond that, the cosmos stretches into darkness, into mystery, into realms where human imagination falters. Humanity's quest to measure the universe has always been an act of cosmic audacity. For thousands of years, people charted stars with nothing more than eyesight and intuition, believing the cosmos to be small, harmonious, and intimate. The universe was once imagined as a crystalline sphere, a dome, a finite bowl containing everything that existed. Even as scientific revolutions shattered these illusions, each new measurement revealed not only greater size but also greater mystery. And each breakthrough raised an unsettling possibility. Perhaps the true magnitude of the universe is not simply unknown, but unknowable. What if every measurement humans make is distorted by forces, structures, or dimensions that they cannot perceive? To explore this idea, imagine the universe not as a single entity with a simple, measurable radius, but as a layered reality with multiple zones, each governed by different physical rules. Perhaps the region humans inhabit is merely a local patch, conditioned by the physics of our cosmic neighborhood. Beyond it may lie regions where the laws of gravity differ subtly, where dark energy behaves differently, or where space stretches at variable rates. If that is true, then any conclusion based on local observations becomes an assumption rather than a certainty. Begin by considering how astronomers currently determine distances. The cosmic distance ladder, a hierarchy of methods ranging from parallax to standard candles to redshift, relies on calibration at every step. If one rung is off, the entire structure wobbles. Tiny errors in the calibration of Cepheid variables can ripple outward, altering distances to galaxies millions or billions of light years away. Variations in supernova brightness can shift estimates of cosmic expansion. If dark energy evolves over time, redshift data becomes distorted. What if these errors accumulate not as minor deviations, but as vast miscalculations? A 1% error in cosmic expansion over 13.8 billion years becomes enormous. A small misinterpretation of redshift could make distant galaxies appear farther than they truly are, or deceptively close. If light behaves differently when traversing regions of space dominated by different forms of dark matter or different quantum fluctuations, then every measurement humans take may be fundamentally incomplete. Now imagine space itself not as a smooth, uniform fabric, but as a dynamic, textured medium. Some theories propose that space-time could be granular at microscopic scales. If so, light traveling across billions of light years may accumulate distortions from interacting with this quantum foam. Each distortion is minimal, but billions of years of travel compound the effect, bending, stretching, or fracturing the wavefront. A galaxy 30 billion light-years away could appear to be 40 billion away, or 20 billion. These distortions need not be symmetrical. Light passing through voids may behave differently from light passing through dense galaxy clusters. Even small variations in gravitational lensing, magnifying, stretching, or bending light, can create impressions of size that differ from the underlying reality. Some scientists have proposed a concept called cosmic variance, the idea that the universe might not look the same in every direction, even on the largest scales. If humans are located in a statistically unusual region, say, a vast underdense void or near an atypical cluster, their perception of cosmic expansion becomes biased. A civilization located elsewhere might measure a completely different value for the Hubble constant. From their perspective, the universe might appear larger or smaller, older or younger. If cosmic variance applies across extreme scales, the universe might lack a single universal size. Instead, size becomes relative, different depending on the observer's location and the surrounding cosmic terrain. Another possibility arises when considering the earliest moments of the universe. During inflation, space expanded faster than the speed of light, smoothing out irregularities and stretching tiny quantum fluctuations into vast cosmic structures. But inflation may not have been uniform. Pockets of space could have inflated more quickly or slowly than others. Some regions may have undergone ultra-inflation, growing beyond any possibility of detection. Others may have inflated only modestly, producing smaller cosmic domains. These pockets may be separated by inflationary walls, regions of space that expanded so rapidly that they now form boundaries between different sectors of the cosmos. If the observable universe lies inside one such sector, it may represent only a fraction of the true inflationary landscape. Beyond the inflationary wall, the universe might look entirely different. Space might be denser, galaxies more massive, physics itself might operate differently. The size of this greater cosmos might be billions or trillions of times larger than the observable bubble humans inhabit. Quantum mechanics further complicates cosmic size through the concept of wave function spread. Some cosmological theories propose that the entire universe is a quantum object, a wave function that extends across multiple realities. If this wave function has no defined boundary, the universe may be infinite in the same way that a wave can stretch indefinitely across an ocean. But humans perceive only the portion of the wave function that decoheres into their observable reality. The true size of the universe, then, lies beyond measurement, not because it is too large, but because it exists in dimensions inaccessible to classical observation. Now consider dark energy, the mysterious force responsible for accelerating cosmic expansion. If dark energy is constant, the universe expands exponentially, forever increasing in size. But what if dark energy fluctuates? If its density oscillates over cosmic time, the expansion rate might accelerate, then slow, then accelerate again. Such fluctuations would distort the relationship between distance and redshift, making faraway galaxies appear as though they have traveled through an inconsistent expansion history. These distortions could make the universe seem larger or smaller, depending on which era of dark energy humans happen to live in. There are even more exotic possibilities. What if the universe is recursively nested, layers within layers, scales within scales? In such a fractal cosmos, patterns repeat across magnitudes. A cluster of galaxies could mirror the structure of clusters embedded in even larger formations. Beyond the largest walls, humans have detected may lie walls of even greater scale, structures so vast that the cosmic web humans observe is merely a microscopic feature. In 3D fractal models, size becomes scale-dependent. There is no definitive edge, only an endless repetition of structure. Some theoretical physicists have proposed that the universe may be a hologram, a three-dimensional reality projected from a two-dimensional boundary. If this is true, size becomes an emergent property rather than an intrinsic one. The universe may appear vast, but the underlying information describing it may occupy far less physical space. Measurements of cosmic size would then reflect a projection, like the apparent vastness of an IMAX screen compared to the thin surface that generates the image. At the other extreme lies the possibility that the universe is far smaller than imagined. If space is curved in a closed topology, light could wrap around the cosmos, creating multiple images of the same galaxy. Humans may be observing the same cosmic structures repeated across the sky without realizing it. If so, the universe might be only a fraction of its assumed size, perhaps just a few billion light-years across, but looped in such a way that it masquerades as enormous. Detecting such topology requires identifying identical patterns across widely separated regions of the sky, a task made difficult by cosmic evolution and limited resolution. Even the cosmic microwave background contains hints, intriguing alignments and temperature anomalies that suggest possible curvature or topology. But these hints remain ambiguous. If the universe loops back on itself, the sky becomes a hall of mirrors, and size becomes a misleading illusion. Another possibility is that the universe is embedded within a larger dimensional framework, a brain within a higher dimensional bulk. In such models, gravity may leak into extra dimensions, explaining its apparent weakness. These extra dimensions could also determine the true size of the cosmos. The observable universe may sit on a 3D slice of a higher dimensional structure, like a bead sliding along a string. Beyond the 3D brain lies a reality whose size dwarfs the observable cosmos. Now, imagine universes budding off from others, forming an eternal chain of cosmic generations. In this scenario, the Big Bang is not the beginning, but a transition, a rebound from a previous universe, or a collision between higher dimensional brains. If such events occur repeatedly, the universe's size becomes part of a cosmic lineage. The universe we observe may be a child of a larger parent universe, and may itself generate offspring universes. In such a multiverse, size becomes a meaningless concept. There is no single universe, only a never-ending network of realities. But perhaps the most humbling possibility is that the universe's size cannot be measured because measurement itself has limits. Humans rely on light as the messenger of cosmic information, but light travels at a finite speed and is subject to distortion, absorption, and stretching. Beyond a certain distance, the universe expands faster than light can travel, preventing any information from reaching us. This is not a technological limitation. It is a fundamental horizon baked into the structure of reality. No matter how advanced humanity becomes, no telescope can see beyond this boundary. The universe could stretch trillions of times farther, or it could end just beyond the horizon. Humans will never know. This limitation forces a profound shift in perspective. The cosmos humans observe is not the universe. It is simply the part accessible to them. Everything beyond that horizon may as well be infinite, because it is forever beyond reach. If the universe is far different from what scientists imagine, then every map, every equation, and every model becomes not a definitive description, but a local approximation, a partial truth about a much grander reality. The true size of the universe might be so vast, so layered, so multidimensional, that humans stand no chance of ever fully understanding it. And yet, the pursuit continues. Not because humans expect to know everything, but because the act of reaching into the unknown is what defines scientific ambition. If the true size of the universe is different from everything scientists have imagined, then every cosmic measurement, every distance ladder, every diagram of the expanding cosmos may be nothing more than an interpretation shaped by our limited cosmic vantage point. Humans observe the universe from a single location in space and time, from a small planet orbiting an ordinary star in the outskirts of a spiral galaxy. From this tiny perch, we try to estimate the size of a cosmos that may be fundamentally beyond the reach of human perception. And the more we learn, the more cracks begin to appear in the illusion of certainty. The first crack comes from the most basic principle of cosmology, the assumption that the universe is homogeneous and isotropic on large scales. Homogeneous means that matter is evenly distributed. Isotropic means the universe looks the same in every direction. These assumptions form the backbone of modern cosmological models. But what if the universe isn't homogeneous? What if its large-scale structure is far more irregular than predicted? If matter is distributed unevenly across ultra-large scales, beyond billions of light-years, then our estimate of the universe's size becomes fatally flawed. Imagine a cosmic landscape arranged not like a smooth ocean, but like a continent filled with mountains, valleys, and canyons. Dense regions expand differently than empty ones. Voids accelerate expansion because they contain less gravitational pull, while clusters slow expansion. If humans happen to live in a massive underdense void, a possibility that some scientists take seriously, then our measurements of expansion would be inflated. The universe might appear larger and older than it truly is, simply because the emptiness around us makes galaxies recede faster. Now consider the reverse scenario. Humanity might live in a region that is unusually dense compared to the cosmic average. In that case, gravitational pull would slow local expansion, making the universe appear smaller and younger than it really is. In either scenario, our cosmic neighborhood deceives us. A single misplaced assumption could distort the size of the universe by billions or trillions of light years. But the problem runs deeper. When astronomers measure distant galaxies, the light they observe has traveled through a cosmic gauntlet. Voids, filaments, dark matter halos, and gravitational wells sculpt the path photons take as they journey toward Earth. Each perturbation alters their trajectory, their wavelength, or their apparent brightness. These distortions accumulate over billions of years, especially over extreme distances. If the universe is filled with structures we cannot detect, dark matter filaments larger than anything we've mapped, supervoids more expansive than expected, or gravitational anomalies in regions far beyond our observational horizon, then every distance estimation becomes a patchwork of guesses. Even the cosmic microwave background, the oldest light in the cosmos, might be warped by these invisible structures. Light behaves predictably only when the space it travels through is stable. But what if the structure of space-time itself fluctuates? What if quantum distortions subtly change the way photons propagate? Over distances of tens of billions of light years, even tiny fluctuations would produce enormous discrepancies. In such a universe, size becomes not a measurable property, but a shifting illusion. Next, consider cosmic expansion. Scientists know the universe is expanding, but how fast and in what manner remains uncertain. The Hubble tension, one of the most significant puzzles in modern cosmology, reveals that two independent methods of measuring expansion produce conflicting results. Measurements of the early universe suggest a slower expansion. Measurements of the modern universe suggest a faster one. No known physics fully explains the discrepancy. If expansion behaves differently in different regions, then size becomes a function of location. A galaxy 1 trillion light-years away might be receding at a dramatically different rate depending on where it lies relative to regions dominated by dark energy or dark matter. In such a scenario, the universe could be far larger or far smaller than currently believed, but because humans can observe only a small region, we mistake a local measurement for a universal one. Another layer of confusion arises when considering the concept of the cosmic horizon. The observable universe is 94 billion light-years in diameter, because that's the limit of the information we can receive. But what lies beyond it? A region where galaxies recede faster than light, a boundary where inflation continues, a multiverse of cosmic bubbles, or an end, a literal boundary of space-time. If the universe extends infinitely beyond the horizon, then the true size is unbounded. The observable universe becomes a tiny island in an ocean without edges. But what if the opposite is true? Perhaps the universe ends not far beyond our cosmic horizon. Perhaps light from distant regions has been bent, curved, or folded around by cosmic geometry, making the universe appear larger than it really is. If space is curved like the surface of a hypersphere, then traveling in a straight line for long enough would eventually bring you back to your starting point. Yet humans might never detect that, because cosmic expansion prevents us from completing such a journey. Topology complicates things even further. Some cosmological models propose that the universe has a non-trivial topology, meaning space could be connected in a complex way, like a three-dimensional donut, Mobius strip, or higher dimensional manifold. In such a cosmic shape, the universe could be finite yet unbounded. It could appear to stretch in all directions while looping back on itself. If this is true, the universe might be only a fraction of its apparent size, with repeated patterns masquerading as distant galaxies. Even more exotic possibilities emerge when considering higher dimensions. String theory suggests that space-time might contain additional dimensions curled up in complex geometric structures. In such a universe, the size perceived by three-dimensional beings becomes misleading. The true volume of the universe may depend on dimensions humans cannot perceive. To beings capable of navigating higher dimensional space, the observable cosmos might appear thin, shallow, or even minuscule, like a sheet of paper compared to a three-dimensional cube. In contrast, the addition of extra dimensions could also mean the universe is far larger than humans can comprehend. A higher dimensional cosmos could contain regions that extend beyond three-dimensional measurement, massive structures, energy fields, or cosmic membranes stretching across dimensions humans cannot access. Now consider the possibility that the universe is part of a multiverse, an ensemble of countless cosmic domains. In some models, each universe inflates independently, like bubbles in a cosmic foam. Our observable universe is one such bubble. Beyond it lie other bubbles, each with different sizes, shapes, expansion rates, physical constants, or even different laws of physics. If this is true, then the size of the universe becomes ambiguous, because universe itself becomes ambiguous. Does one measure the size of our bubble, or the size of the entire multiverse, or the size of the hyperreality that supports the multiverse? A small universe inside a vast multiverse might be as insignificant as a droplet in a cosmic storm. Conversely, our bubble could be enormous by multiversal standards, stretching across unimaginable distances relative to other realms. In such a scenario, size loses meaning. There is no largest or smallest, only relative scales, each defined by the physics of its domain. Then comes the philosophical dimension. What if the universe's size is fundamentally unknowable due to the nature of measurement itself? Light has a finite speed. Signals weaken, distort, and fade. Expansion stretches wavelengths to invisibility. No matter how advanced future instruments become, they cannot overcome the cosmic horizon. Information from beyond that horizon will never reach Earth because space expands faster than light can travel. This creates an eternal boundary between the observable universe and the unobservable reality beyond. Thus, the universe might be infinite, finite, looping, layered, or multiversal, but humans can never see or confirm any model that extends beyond the cosmic horizon. Perhaps the universe is simply too large for human cognition to grasp, or perhaps it is too multidimensional, too dynamic, too deceptive, too fundamentally alien. Yet despite these impossibilities, perhaps because of them, humanity continues to measure, theorize, and imagine. The cosmos rewards curiosity with glimpses of truth, even if those truths are fragments of a much larger, hidden structure. The real universe may be far larger, or far smaller, or far stranger than any scientific model. It may be shaped by dimensions humans cannot sense, by forces they cannot detect, or by physics they cannot conceive. But the limits of perception do not diminish the value of the pursuit. The act of reaching into cosmic darkness is itself a triumph, a declaration that humans will not be confined by ignorance, even if ultimate answers remain forever beyond our grasp. What if the universe we observe is only a single layer of a much deeper cosmic structure, one so vast, so complex, and so fundamentally alien that every scientific measurement made so far reflects only a shadow of the true reality? What if humanity's perception of the universe's size is shaped less by the cosmos itself and more by the limitations of human senses, instruments, and assumptions? To explore this possibility, we must follow a thread of reasoning that leads into the most profound and disorienting ideas modern science has ever proposed. Begin with the assumption that humans observe the universe using light, photons emitted by stars, galaxies, quasars, nebulae, and the faint afterglow of the Big Bang. Light, however, is not an impartial messenger. Its journey across the cosmos is influenced by gravity, matter, energy, and the shape of space-time itself. Imagine trying to judge the size of an unfamiliar city by watching shadows cast by passing cars on distant buildings. The shadows stretch, bend, blur, and distort depending on the angle of the sun and the terrain of the landscape. If the city were irregular, filled with hills and valleys, the shadows would give wildly different impressions depending on where you stood. This is precisely the challenge astronomers face when measuring the cosmos. Every piece of information is filtered through cosmic terrain that humans cannot see directly. The cosmic microwave background, the oldest light in the universe, serves as a kind of blueprint for cosmic structure. But even this ancient radiation is not immune to distortion. As its photons traverse billions of light years, they pass through clusters, filaments, voids, and regions rich in dark matter. These structures gravitationally lens the primordial light, subtly altering the temperature fluctuations imprinted upon it. If these distortions occur on scales larger than anticipated, or across regions beyond the observable universe, then our interpretations of the cosmic blueprint become skewed. A universe that appears 94 billion light-years across might be far larger or smaller, depending on the cumulative effect of these distortions. Now consider inflation, the brief period of hyperexpansion that took place in the first fraction of a second after the Big Bang. According to the simplest inflationary models, the universe expanded exponentially, smoothing out irregularities and shaping the cosmic structure we observe today. But inflation is not a simple process. It may have proceeded differently in different regions. Some pockets of space could have inflated more rapidly, growing to sizes unimaginably large. Others might have inflated only modestly, becoming isolated cosmic islands. Our observable universe could be one such island in an archipelago of countless cosmic regions. If this is true, then the size of the observable universe tells us nothing about the size of the actual universe. A region that expanded far faster than ours could lie just beyond the cosmic horizon, receding at speeds that prevent its light from ever reaching us. Conversely, our region might be unusually large compared to others, giving us the false impression that the cosmos is enormous, when in fact, we inhabit an anomalously inflated domain. Even more intriguing is the possibility that inflation never truly ended. In some models, inflation continues eternally in the multiversal background, creating new universes, like bubbles in a cosmic foam. If our universe formed as one such bubble, then its size becomes relative to the multiverse. A large or small universe loses meaning when compared to domains that might be infinitely larger or unimaginably smaller. But the story grows stranger when we consider the curvature of space. If the universe is positively curved, like the surface of a sphere, then it could be finite, yet have no boundaries. Traveling in a straight line long enough would return you to your starting point, but expansion prevents us from completing that circuit. If the universe is curved in this way, the light we observe could be looping around, giving us multiple images of the same galaxies. Our measurements of size would then be inflated by illusions created by cosmic topology. Conversely, if the universe is negatively curved, shaped like a saddle, then its true scale could be far greater than its observable extent suggests. Both possibilities challenge the assumption that space is flat. Yet measurements of the cosmic microwave background appear to show flatness at large scales. But this measurement applies only to our observable region, not to the totality of space-time. The cosmos beyond the horizon may curve dramatically, creating a mismatch between local observations and global structure. This leads to the question of dimensionality. Humans experience space as three-dimensional and time as one-dimensional, but physics allows for additional dimensions, curled, hidden, or stretched across scales we cannot perceive. If extra dimensions exist, they may fundamentally affect the size of the universe. Imagine a two-dimensional creature living on a flat sheet of paper. To that creature, the sheet is the entire universe. It cannot perceive the third dimension in which the paper is folded or rolled. If the sheet is bent, curled, or wrapped around another object, the creature's idea of size is based solely on the flat plane it can inhabit. Likewise, humanity might be confined to a three-dimensional brain floating within a higher dimensional bulk. The universe may appear enormous in 3 dimensions but small, or gigantic, when measured in higher dimensions. Our cosmic horizon could be the equivalent of the edges of the paper, while the true universe extends far into higher dimensional space. In this model, the universe could be extraordinarily small in the bulk, even if it appears vast in our 3-dimensional perception. Or it could be incomprehensibly large, stretching across dimensions that dwarf our observable cosmos. The idea of size becomes not merely relative, but dependent on dimensional context. Quantum mechanics complicates this further. According to the holographic principle, the entire universe might be encoded on a 2-dimensional boundary at its outer surface. The size of the universe, then, is not a function of its volume, but of the information stored on its boundary. What appears to be an enormous 3-dimensional cosmos might actually arise from processing occurring on a much smaller surface. This would render cosmic size an emergent illusion rather than a fundamental property. Even the nature of space-time could distort our perception. If space-time fluctuates at quantum scales, then distance measurements become probabilistic. Over billions of light-years, these quantum uncertainties compound, producing measurable distortions. 2 galaxies separated by a fixed distance might appear increasingly separated as these uncertainties grow. Cosmic expansion might be partly real, partly an emergent effect of quantum-scale fluctuations integrated over cosmic distances. Dark energy, the mysterious force driving the acceleration of expansion, may also play a role in distorting cosmic size. If dark energy's intensity varies across different regions, then expansion rates might differ dramatically. Distant galaxies could appear farther away, not because they truly are, but because they lie in regions where dark energy has grown stronger. Conversely, regions with weaker dark energy might compress cosmic distance. In such a universe, size is not static, but evolves with the changing behavior of dark energy across the cosmic web. Now consider gravitational lensing effects from structures beyond the observable universe. If massive superclusters or supervoids lie past the cosmic horizon, their gravitational pull could warp the path of photons reaching us, shifting images and altering perceived distance. Entire regions may appear stretched, magnified, or elongated due to unseen gravitational influences. In this sense, the observable cosmos becomes a funhouse mirror shaped by structures humans cannot detect. Another possibility is that the universe contains anisotropic expansion, expanding at different rates in different directions. If true, the observable universe might be a distorted patch of a much more complex expansion field. Some directions might lead toward regions of slower expansion, others toward faster expansion. The true size of the universe, then, depends on the direction in which one measures. Even time itself might distort cosmic measurement. If time flows differently in different regions due to varying gravitational potentials, then the redshift measurements used to estimate distance become flawed. A galaxy's apparent distance might reflect time dilation rather than spatial separation. Humans could be misinterpreting cosmic time variations as spatial expansion, vastly overestimating or underestimating distances. Finally, there is a possibility, even more unsettling, that the universe has no meaningful size at all. Size may be a human-imposed concept that does not apply to the fundamental structure of reality. The cosmos might not have boundaries, edges, or limits in any conventional sense. It may not be finite or infinite, but something beyond those categories, structured in a way that defies classical geometry. In such a universe, asking for the size of the cosmos is like asking for the weight of a color or the temperature of an emotion. The question breaks down because the concept itself does not apply. Yet despite all these possibilities, despite the uncertainty, the distortion, the quantum fluctuations, the multiversal scale, the dimensional complexity, humans continue to measure, model, and imagine. The search for the universe's true size is not only a scientific pursuit, but a philosophical one. It challenges humanity to confront the limits of perception and the boundaries of imagination. If the universe is far larger or far smaller, more curved or more multidimensional, more layered or more fragmented than anything scientists have envisioned, then the quest to understand it becomes the ultimate adventure, a journey into a realm where knowledge expands faster than the cosmos itself. If humanity ever discovers that the actual size of the universe is fundamentally different from everything scientists have imagined, the revelation wouldn't just rewrite textbooks, it would redefine existence itself. It would challenge the very framework through which we understand reality. Yet the deeper we look into the cosmos, the more one unsettling truth becomes clear. Every measurement of the universe's size is built upon assumptions that may not hold at the deepest levels of physics. The cosmos might not be larger or smaller than we think. It might be something entirely beyond the concepts of large or small. It might be structured in a way that makes these words meaningless. To understand why, imagine stripping cosmology down to its foundations. Our perception of cosmic scale relies on four pillars: the speed of light, the expansion of space, the uniformity of physical laws, and the behavior of gravity. If any one of these behaves differently than we assume, even slightly, the size of the universe could shift by unimaginable magnitudes. And if all four deviate across vast distances, our entire notion of the cosmos becomes a distorted projection. Start with the speed of light, often treated as the universe's ultimate constant. But what if the speed of light wasn't always the same? Some theories propose that in the early universe, light traveled far faster than it does today, a solution to several long-standing cosmological puzzles. If true, the cosmos might be smaller than we think, because early light could have crossed distances far more rapidly, reducing the effective size required to explain the uniformity of the cosmic microwave background. Conversely, if light slows incrementally across unfathomable distances due to interactions with vacuum energy or quantum fluctuations, then galaxies might appear more distant than they truly are. Even a minuscule change in the speed of photons, integrated over tens of billions of years, could inflate or compress our cosmic map. Now consider gravity. Einstein's general relativity describes how massive objects curve space-time, but the theory has never been tested on scales of hundreds of millions or billions of light years. Observations show gravitational anomalies even on galactic scales, flat rotation curves, lensing discrepancies, mass deficits that we explain using dark matter. But what if dark matter isn't the answer? What if gravity itself behaves differently on cosmic scales? Modified gravity theories propose that gravitational attraction weakens or strengthens over extreme distances, altering the large-scale structure of space-time. In such a universe, distance measurements based on gravitational effects could be wildly inaccurate. Structures that appear billions of light years apart might be closer or farther, depending on how gravity truly operates across the full cosmic web. Then we confront dark energy, the mysterious force driving the acceleration of cosmic expansion. Current models treat dark energy as a uniform property of the vacuum, but what if it isn't uniform at all? If dark energy fluctuates across space or evolves over time, different regions of the cosmos could expand at different rates. The observable universe might be a pocket of rapid expansion, surrounded by regions of slower growth, or regions of ultra-fast inflation so extreme their light can never reach us. In such a scenario, size becomes entirely regional. Our cosmic bubble might be just one zone in a stratified expansion field, like a patch of warm air in a turbulent atmosphere. The true universe could be colossally larger, but expanding so violently in certain regions that no signal can ever cross the boundary. Or it could be smaller, with inflation merely creating the illusion of vastness. The cosmic horizon, the farthest limit of what we can observe, adds yet another layer of uncertainty. Our horizon marks the maximum distance light has traveled since the Big Bang, but beyond that horizon may lie regions of space that obey different physics. If their expansion rate, density, curvature, or time flow differ from our own, those regions might be physically disconnected from us. We may inhabit a cosmic island, separated by expansion rather than ocean. In this case, the universe may not simply be larger, it may be compartmentalized, divided into sectors that cannot interact. The idea of a single universal size disintegrates. We might live in one cell of a cosmic honeycomb. Now consider topology, the shape of the universe itself. A universe that appears flat on observable scales could curve dramatically on larger ones. Like an ant walking on the surface of a balloon, humans may mistake a curved space for a flat one, simply because they have explored only a tiny region. If space loops back on itself, then the cosmos could be far smaller than assumed, with repeated images of galaxies masquerading as distinct objects. If space spirals, twists, or folds in higher dimensions, its effective size becomes impossible to visualize using three-dimensional intuition. A universe shaped like a torus, a Mobius loop, or a higher dimensional manifold could contain distances that bend back into themselves, collapse, or extend outward depending on the observer's direction. Quantum mechanics complicates the picture further. Quantum foam, the jittering, fluctuating fabric of space-time on the smallest scales, could create cumulative distortions over large distances. Light traveling across billions of light years might pick up quantum noise, altering its wavelength unpredictably. These distortions could mimic cosmic expansion, exaggerate redshifts, or scatter photons in ways that trick astronomers into overestimating distances. In such a universe, size becomes smeared, blurred, probabilistic. The cosmos might not have a single definable radius, but instead exhibit a distribution of possible sizes depending on quantum uncertainties. Then comes the multiverse hypothesis, the idea that our universe is just one of countless cosmic domains. In some models, universes continuously bud off from others in an eternal inflation process. In others, each universe exists as a separate solution to fundamental equations, occupying its own region of a higher dimensional landscape. If the multiverse is real, the question, how big is the universe, becomes ambiguous. Do we mean our observable patch, our entire inflationary bubble, the whole inflating background, or the complete multiverse? Depending on the answer, the size of the universe could range from 94 billion light-years across to infinite beyond comprehension. The true size might even be unbounded in dimensions humans cannot perceive. Even consciousness and perception might play a role. Some physicists argue that space-time emerges from patterns of quantum entanglement. In this view, the fabric of the universe is not a physical arena, but a construct arising from information. If so, the size of the universe depends on how information is distributed and how observers interact with it. Space might be emergent, not fundamental. Time might be emergent. Distance might be emergent. The universe might not even exist in the classical sense without observers to collapse its wave functions into definite structures. This raises an unsettling possibility. The size of the universe might not be a property of the universe, but a property of observation. Different observers, different civilizations in different regions, might measure different cosmic scales because their local information environment defines their observable reality. The universe might be vast for one civilization, compact for another, infinite for a third. Size becomes an observer-dependent illusion rather than an objective quantity. Finally, consider the ultimate possibility that the universe is fundamentally unknowable. The cosmic horizon is not a technological barrier. It is a physical limit encoded into the nature of space-time. No telescope, no signal, no breakthrough in physics can reveal what lies beyond it. We cannot see past it because nothing, not even information, can cross that boundary. In such a cosmos, the true size of the universe is not merely unknown, but unreachable in principle. We live inside a bubble of information, and everything beyond its boundary might as well be infinite. This limitation does not diminish the human quest for knowledge. It elevates it. Knowing that the universe might always remain partly hidden forces us to confront the humility of our position in existence. Yet within that humility lies a remarkable truth. Even from a tiny planet circling an ordinary star, humanity has measured the age of the cosmos, mapped billions of galaxies, detected ripples in space-time, and traced the evolution of the universe from its first fraction of a second. If the universe is far larger, far smaller, more dimensional, more fragmented, or more unfathomable than we imagine, then every step we take toward understanding becomes an act of cosmic courage. Thank you for watching. If you enjoyed this video, leave a like and share your thoughts in the comments. Send it to someone who you think would enjoy this topic too. And of course, subscribe and turn on the notification bell so you don't miss the next videos. See you next time.